Hello everyone, this is Professor Roman. Let's continue the field theory lectures. We have discussed two parts of the fundamental theorem of Galois theory. The first concerned the correspondence itself, and we saw that the restricted Galois maps, that is to say the Galois maps whose domain and codomain are restricted to the closed elements, are degree-preserving inverse lattice anti-isomorphisms. It's quite a mouthful. The second part of the fundamental theorem of Galois theory concerned which elements of the correspondence are closed. We saw in particular that for a finite Galois extension, all of the elements on both sides, the field side and the group side, are closed. And the third part of the fundamental theorem of Galois theory, which we're going to discuss now, concerns normality. For this discussion, let's make an observation about the conjugates of a Galois subgroup. So suppose we have a two-tower of fields, and it's algebraic. Then for any sigma in the Galois group of the full extension, if we conjugate the Galois group of E over K, the intermediate field, we conjugate it by sigma, we get the Galois group of sigma K. We get the Galois group of E over sigma K. And the proof looks like this. For an element A and K, conjugate the Galois group of E over K and apply any of those automorphisms to sigma A. The conjugate of GKE is sigma GKE sigma inverse. Apply that to sigma A. The sigma inverse and sigma cancel. We get sigma GKE A, but A is in K, and so it's fixed by every automorphism in this Galois subgroup, so this is just sigma A. And so the conjugate of GKE fixes any sigma A. Or I should say, I guess, sigma of any A in K. So it fixes A capital K. These are automorphisms of E that fix sigma K. So we have this inclusion. On the other hand, if A is in K, then G sigma K E conjugated by sigma inverse applied to A is sigma inverse G AKE sigma A, but anything in G sigma KE fixes sigma K element-wise, and so sigma A is fixed, so we get sigma inverse sigma A, and that's A. So the elements in here fix everything in K point-wise. And so we have this inclusion conjugating by sigma gives us this inclusion, which is the reverse of this one, and so we have this equality. This isn't as bad as it looks. If you go over it a couple times, it shouldn't be too bad. Well, as we have seen, the Galois correspondence is a correspondence between intermediate fields and subgroups of the Galois group. On the group side of the correspondence, there's a property that is undoubtedly the single most important property of subgroups of a group, and that is normality. So, it's natural to wonder how this property, normality of subgroups, of Galois subgroups in particular, is reflected on the field side of the correspondence. Most of what we concentrate on is reflecting properties on the field side to the group side. But here we're going in the other direction. Now, we already have a hint because we've been using the term normal extension for quite some time. But that terminology is a benefit of precognition, of looking ahead to what we are doing now. So we really should set that aside. We should pretend that what we've been calling normality for a field extension has some other name, because when we first introduced it, we had no idea that it was connected to normality of Galois subgroups. In fact, we hadn't even defined the Galois groups yet. I could have used a different term than normality throughout, but normality is a standard term, and so I decided to stick with it. Could have called normal extensions splitting field extensions instead, and then at this point we would tie splitting field extensions to normality on the group side, and then say, well, that's why splitting field extensions are also called normal extensions. Actually, that's not such a bad idea, but as long as you understand what I'm saying, it doesn't matter that we use the term normal extension well before we define the Galois correspondence. I think I even mentioned that the reason they're called normal extensions is because eventually we will show that there's a connection between normal extensions and certain normal subgroups of the automorphism group. In any case, let's continue. So suppose that Fe is a Galois extension and K is an intermediate field. Theorem 525, which we just discussed here, the conjugate of a Galois subgroup, and the fact that all intermediate fields of the Galois correspondence are closed because we have a Galois extension. So all intermediate fields, K here, for example, Ke is also Galois. Okay. And so K is closed. I'm not talking about the group side now. I didn't say this had to be a finite Galois extension. We're just talking about the field side. So we can say that GKE is normal in GFE if and only if, by definition, any conjugate of GKE is itself, where sigma ranges over the full group here. Okay, so GK is closed under conjugation. That's normality. And the result we just talked about conjugates, this is equivalent to G sigma KE equals GKE. And now, because the full extension is Galois, all the intermediate fields are closed, we can take fixed fields of this, and we will get sigma K equals K for all sigma in GFE. Okay? So we have an equivalent condition for the normality of GKE in the full Galois group. On the other hand, we had a theorem some time ago concerning the normality of the lower step in this tower. And we saw that Fk is a normal extension if and only if the restriction of the elements of GFE, the full Galois group, restriction to K is the Galois group GFK. And that was also equivalent to sigma K equals K for all sigma in GFE. Well, that's what we have here. So these two are the same, and therefore FK is normal if and only if GKE is normal in GFE. So we've done the heavy lifting. We did it way back in chapter 2, and also we just did a little bit when we took the conjugate of a Galois subgroup, just piecing everything together, and we have a result that we really would desire. And it looks like this. So the picture, this extension, this lower step here is normal if and only if GKE is a normal subgroup of GFE. Okay? You wouldn't expect a relationship between the lower step here and something at the bottom end of the group side, because Galois maps are order reversing, so this is what we would expect to see. Okay? And in fact, GKF is not even in this picture, the Galois group of the extension, the lower extension here, because the domains of these automorphisms are E, not K. Right. That's something to think about if you're at all confused about that. Well, there's a little more, or a lot more maybe, we can say here, not beyond the fact that normality of the lower step is equivalent to normality of the Galois subgroup in the full Galois group. Another way to phrase normality here, another way to phrase this part, is that FK is normal if and only if the restriction map restricting GFE to K, now we are mapping into GFK, which is here, that this is a surjective map. Oh, I'm sorry, my fault. Okay, so let me say again. This is equivalent to this. This says that this map is surjective. Moreover, the restriction map, for restriction to K, is a group homomorphism, and that's here. This is something you should do yourself. And here is the kernel, which it happens to be GKE. So the first isomorphism theorem of group theory tells us that this restriction map induces an isomorphism from this quotient to this Galois group. So let's go back to the picture. Well, actually, yeah, let's go back to this picture. So I said that GFK, let me write it down, GFK is not in this picture, which is true. All these Galois subgroups are of the form G something down here, E, because they're automorphisms of E that fix something. But this does appear as the quotient group. Okay. So the Galois group of this lower step is not on here, but it is isomorphic to this quotient. This is normal because this is normal. We're assuming this is normal, therefore GKE is normal in GFE, so the quotient set is in fact a quotient group, and it's isomorphic to this Galois group. So we can now state what I just said as the third part of the fundamental theorem of Galois theory. Here's a picture. This is a tiny bit more general than the previous picture because I wanted to have an intermediate extension here. See, in this picture, the base field is F, but I wanted to have an arbitrary base field K somewhere in between here. So if this is normal, if and only if this is normal, and notice how things are reversed here. K is below L here, but L is below K because of the order reversing nature of the Galois maps. This is normal if and only if this is normal, in which case the Galois group GKL is isomorphic to the quotient. So it's this mod this. That is the third part of the fundamental theorem of Galois theory. Okay, we have a Galois extension. We have a couple of intermediate fields. So we have a three tower. And as shown in this figure, the intermediate step is normal if and only if the Galois group GLE, remember these have to be E's, the Galois, if and only if GLE is a normal subgroup of GKE. So that's what this is. Or another way to say it is that this extension is normal if and only if the restriction to L map is surjective. And in that case, it's a group homomorphism. This is its kernel, and we have this relationship, this isomorphism. Okay, I know that three parts of the fundamental theorem of Galois theory is a lot to absorb. But I broke it into three parts in hopes that at least you could say, well, the first part is about the basic properties of the Galois maps and what happens when you restrict them to closed elements. The second part is about who's closed, and the third part is about who's normal. Okay, so maybe that'll help compartmentalize all of this a little bit. Here's an example of the use of the third part. We need a definition, a Galois field extension. This is a very important definition, by the way, for us later. A Galois field extension is abelian or cyclic if the Galois group is abelian or cyclic. So it's a pretty straightforward definition. We're just borrowing some group theory terminology and sticking it on the extension, just as we did with normality. Theorem. If we have a Galois extension Fe, if the full extension in a tower like this is abelian or cyclic, then so are the steps. Proof, since the full Galois group is abelian or cyclic, all subgroups of the full Galois group are abelian or cyclic. So this is really two theorems, one about abelianness and one about, how does one say, cyclicness. But rather than repeat this all twice, I just did it this way. And so we're either talking about abelian or cyclic. In particular, then, this applies to GKE. All subgroups are abelian / cyclic, and so GKE is abelian or cyclic. And that means by definition that the upper step is abelian / cyclic. that's not big news. It's the other part, the lower step. GKE is also normal in GFE. And so this quotient we get from the third part of the fundamental theorem of Galois theory tells us that GFK is abelian or cyclic, because we're taking a quotient here. And so that preserves abelianness or cyclicness. So the lower step is abelian or cyclic. So it's the third part of the fundamental theorem that gives us the information about the lower step being abelian or cyclic. This will tie into solvability by radicals, which is why it's so important for us.